Hey guys, so this video is going to be on Bronsted-Lowry acids and bases, as opposed to the Arrhenius acids and bases that we were talking about. So this is the way that Bronsted and Lowry defines acids and bases. It's just in a different context, in a different point of view than Arrhenius. So it happens that most Arrhenius acids are Bronsted acids as well. But not all Arrhenius bases are Bronsted bases. So we'll see what I mean. Let's take a look at our book. Okay, so this is from section 8.4, Bronsted-Lowry and acids and bases. So as we can see, the Arrhenius definition is that you have to have hydronium generation when added to water. And the Arrhenius base definition is that you generate hydroxide when added to water. For Bronsted-Lowry bases, you do the same. However, you are thinking of the proton. So think of an acid definition as a proton donor and the base definition as the proton acceptor. So here's three examples here. So you can see in the top example, we have ammonia plus acetic acid, which is HC2H3O2. So according to Bronsted-Lowry, right, the acid is the one that donates the proton and the base is the one that accepts it. So the first thing you want to do is identify which one is the base and which one is the acid. And then it's quite easy to figure out what the products are. So NH3, right, we already saw from another video that is a base, right? And this, you should know, is your oxoacid acetic acid, right? So HC2H3O2 is going to be the one that donates the proton. So it's going to take H, here, just take the H plus and put it onto NH3. So what does it become? NH4. But remember, you're not just donating a hydrogen, you're donating an hydrogen plus, an H plus. So therefore, NH4 is now a cation as well, right? So if you give NH3 an H plus, it becomes NH4 plus. And then what do you have left over after the acetic acid loses its proton? You just have C2H3O2 negative. Okay. Now let's look at this one, water and acetic acid. Now water is a really interesting molecule. Water is called amphoteric because water can act as both a Bronsted-Lowry acid and base. So when water sees an acid, it will act as a base. And when it sees a base, it will act as an acid. And these next two examples is going to show you that. And again, the term is called amphoteric. So water is amphoteric. Okay, let's look at this second line, water plus acetic acid. So H, right, leads with H. We know that this is the acid. So this is going to be your proton donor. So move that H plus to water, right? H plus H2O will give you H3O plus. And then what's left over is C2H3O2 negative, okay? So make sure you see that. You know, this is one of the, I'm sure this is the first time that you've seen such a reaction. Try to work that out and see how that makes sense, all right? All right, the third line, we have ammonia, NH3, which we know is a base. And so when water sees a base, it's going to act as an acid. So now water is your acid, okay? So make it lose a proton and give it to NH3 because it's the base that accepts the proton, right? So your water is going to donate its H plus. NH3 takes the H plus and becomes NH4 plus, right? And then what happens if you take H plus away from water? Well, you have OH minus. Okay. And so you see the formation of hydroxide here, right? From ammonia being in water through the donation of the proton to the ammonia. Okay. So we can call these reactants here BL base and BL acid. And then we can think about the backwards reaction. So let's do this. NH3 plus H2O goes to NH4 plus OH minus. So if this is your base and this is your acid, now do you think about the reaction going in reverse? Then it's NH4 plus that is losing the proton. You see that? So NH4 plus will lose the proton to become NH3, while OH minus will gain the proton to become water. So this is why we call NH4 plus the conjugate acid, and we call this one the conjugate base. Okay, so you have that relationship where the base and the acid come together to make the conjugate acid and the conjugate base. Okay. And so these pairs here, NH3 and NH4 plus, this is called a conjugate acid base pair. Okay. And then the other conjugate acid base pair would be water and hydroxide. Okay. Okay, so let's go back and do some example problems here. So let's take a look at this one. Identify the Bronsted-Lowry acid and base for the Ford reaction in each of the following equations. And also, let's practice naming the conjugate acid and the conjugate base. So let me just put those reactions on the board, and then we are going to do them together. Okay, so for each of these, we're going to identify the acid, the base, and then the conjugate acid and the conjugate base. Okay, so in A, okay, we see that HClO2, that must be the acid, right? That must be the acid. And then here, your sodium IO, that's going to be the base, because the sodium is the sodium plus and the IO is minus. So if this is the acid, this has to be the base. And then we basically just follow the proton, right? Because that's the definition. The Bronsted-Lowry definition of an acid is a proton donor, and the base is the proton acceptor. So once you have it labeled, it's pretty easy to just move the proton. So let's move this proton over here. Okay. So you're going to have HIO, and then what's left is sodium chloride. So HIO plus sodium chloride, right? So that H plus moves over here, right? And then the sodium plus goes with the ClO2 minus. Remember that that is your polyatomic, okay? So to say which one is the conjugate acid and which one is the conjugate base, look at these as now the reactants going backwards this way. So if we go backwards this way, we see that it's this one that gives up the proton, right? So this must be the conjugate acid because that donates the proton. And who gains it? The ClO2 gains that proton. So this one is going to be the conjugate base. Okay, let's do another one. B, HS minus plus HF goes to H2S plus F minus. Okay, so in this case, we see that this HS minus is the one that gains the proton to become H2S, right? That's what happened. So this one must be the base because it accepted the proton, right? And HF must be the acid. Okay, so now to label these, think about again, going backwards, who's losing the proton and who's gaining it? Going backwards, it's F minus that gains the proton, and it's H2S that loses the proton. So H2S is the conjugate acid, while F minus is the conjugate base. C, HS minus plus OH minus is S2 minus plus water. So as you can see, who's losing the proton? It's the HS minus that's losing the proton, okay? And it's OH minus that is gaining it. So this is going to be your base, and this is going to be your acid. Okay? So now going backwards, you can see that it's the S that is gaining the proton to become HS, right? And it's the water that's losing the proton to become hydroxide. So that means going backwards, S2 minus is the conjugate base, while water is the conjugate acid. Okay. So that's what you should be able to do, is to label acid base and then label the conjugate acid and the conjugate base. Okay, let's do it for D. Maybe you guys want to try, doing this on your own. Pause the video and then see if you get the right answer here. So in this problem, we see that H3ASO4 goes to ASO4. Okay. So that means it's lost the proton. So this will be the acid. This is the base. Okay. And this will be the conjugate base. And this is the conjugate acid. Okay. Okay, let's do this problem here. Write the formula for the conjugate acid of F minus, NH3, HSO4 minus, and CrO4 minus. Okay, let me write that on the board first, and then we'll solve. So it wants the conjugate acid of F minus, NH3, HSO4 minus, and CrO4 minus. Okay. So to get the conjugate acid, what you need to do is add a proton, right? Because it wants the acid version of this. Okay, the acid version of it must have a proton, right? So anytime you're asked for a conjugate acid, add a proton. So just add a proton to this. For A, it would be HF, right? A proton is H plus, right? So H plus and F minus will be neutral, HF. Now for B, you have NH3 and you're going to add an H plus. So what does that become? NH4 plus, right? It's an NH3 plus an H plus. So you're not only absorbing a hydrogen, you're also absorbing the positive charge, right? So you become NH4 plus. C, HSO4 minus. You add a proton to that. Well, then you'd have two now, right? So H2SO4, but you also add a plus sign. So a plus sign, but it's HSO4 minus. So a plus sign and a minus sign neutralizes out. So H2SO4 neutral. Okay. D, you have CrO4 minus. Okay, so notice that charge. You're gonna add a proton to that. So what do you get? You have an H CrO4, but now the 2 minus becomes a 1 minus because plus and 2 minus, right? 2 minus and a plus is a negative. So don't forget that. Not only are you adding the atom, but you're also adding the charge. Okay. Good. Now, what if I ask you for conjugate base of things? So let's say I want the conjugate base of water. I want the conjugate base of carbonate anion. Not carbonate, bicarbonate HCO3 minus. What if I want the conjugate base of H2SO4? And then the conjugate base of H2PO4. Let's do let's do HPO4 2 minus. Okay. All right, so now since it wants the conjugate base, remember that you want the version where the proton is lost, right? Because that's what a base does. A base is right, the base accepts the proton, right? And so if you want the conjugate base, you want to make it lose a proton. Okay. So the conjugate base, make it lose a proton, becomes OH minus, right? So take water, subtract an H and a positive sign, right? So get OH minus. B, you take away a proton, that H is going to H plus. So that H is going to go away. So you have CO3, 2 minus, right? Right? Remember, you're taking away, you're subtracting an H plus, right? And so the minus becomes a 2 minus. Okay? C, in H2SO4, you subtract an H plus as well. So you have HSO4 minus. Okay? And then D, you subtract an H plus, the H goes away. Subtract an H plus, this gets more negative because you're taking away a plus sign, so you make things even more negative, right? So it becomes PO4 3 minus. Okay. Okay, so now if you were to ask, write the conjugate acid-base pairs of these things, you would just pair them together, right? So water and hydroxide is considered a conjugate acid-base pair. HCO3 minus and carbonate is considered a conjugate acid-base pair. H2SO4 and HSO4 minus is considered a conjugate acid-base pair. And HPO4 2 minus and PO4 3 minus is considered a conjugate acid-base pair, right? So you can imagine there are many examples of conjugate acid-base pairs, right? And basically all that is they differ by 1 proton, right? That's their relationship, is they just differ by 1 proton, right? So in summary, okay, let's summarize. If you're asked for the conjugate acid, then add a proton. If you're asked for the conjugate base, then remove a proton. And so that's all, right? That's all. Okay. All right, guys, I'll see you in the next video.